Hi everyone, today we're going to be talking about water's unique properties and where we see it occurring in our lives.
One unique property of ice is that it's less dense as a solid than as a liquid. We see this every day when we get a glass of ice water.
So, why does that happen?
I don't know, let's find out. Goodness. Hey look, Kendall, I found something.
Me too. Did you see the section about hydrogen bonding?
I wasn't looking at that. I found phase diagrams that answer questions.
I wonder if they're related.
They probably are. Everything in chemistry is related one way or another. Let's start teaching about hydrogen bonding first.
Alright, so basically, hydrogen bonding occurs when a hydrogen atom bonds to a nitrogen, oxygen, or fluorine atom, which means that hydrogen bonding occurs in water. Therefore, its ordinary solid phase does not have the close-packed structure. Molecules in water take up extra space in order to make their hydrogen bonds line up so they have a more stable solid. So, ice molecules look a little something like this.
Oh, I see where you're going. So when ice melts, the hydrogen bond structure will collapse, causing the liquid to be more dense than the solid.
Exactly! So that's why hydrogen bonding in water is so important to its properties. Now, where are you going with phase diagrams?
Well, the phase diagram of water is pretty different than a typical phase diagram.
Whoa. Back up. Don't you think we should explain to everyone what a phase diagram is first?
That would probably be a good idea. So a phase diagram has temperature on the x-axis.
And it has pressure on the y-axis.
Yep. It shows us at what temperature and pressure a substance will transition into different phases. So each substance has a different phase diagram. So this is what a typical phase diagram looks like with this line. So this is where the substance is gas, liquid, and solid.
Alright, so this seems simple enough, but what's that point right there?
That's the triple point.
The what?
The triple point is where the substance exists at all three phases.
Okay, that makes sense. What about this point?
That's the critical point. The critical point is the highest temperature at which you can have a conversion from gas to liquid. After this, it's just gas.
Okay, cool. So now that they know the basics of phase diagrams, we can go back to talking about water.
Alright, so the phase diagram of water is this line. The rest of it is pretty much the same general idea.
So, in a typical phase diagram, the slope of the melting point is positive, right here. This means that an increase in pressure will require a higher temperature for the substance to melt.
However, with water we see that the melting slope is negative. This means that when pressure increases, the temperature of the melting point is actually lowered, which is pretty cool. But how does this relate to hydrogen bonding?
Well, I think to justify the negative slope with the idea of bonding, we need to bring in Le Chatelier's principle.
Le Chatelier's principle states that when a system is in equilibrium, any external changes that try to take it out of equilibrium,
such as applying pressure to ice,
will cause the system to adjust in a way to counteract that change.
So if you increase the pressure on ice, the system will want to lower it again. It can do that by making itself fit into a smaller volume. But since water fills a smaller volume than its liquid, rather than solid due to the density, it will go to a lower melting point and will allow more solid to become liquid.
So that's where the hydrogen bonding comes in. Because of those spacious hydrogen bonds, ice will turn to water to minimize the stress on its system. Neat.
Exactly.
Okay, wait. We told them that this stuff appears in everyday life, but I don't get the connection.
Well, I'm about to show you. Close your eyes.
Whoa. Why are we at an ice rink?
Oh. So Grace just got my point, but you guys might be still confused on why we're in an ice rink.
So, when a figure skater is on the ice, her entire weight is put into her blades, typically about 0.15 inches thick, and is about as long as a skater's foot.
Alright, so the large amount of pressure that causes the ice to have a lower melting point, allowing the skater to increase mobility of the blade and glide smoothly across the ice. So when you're watching the Winter Olympics, you're also watching chemistry in action.
However, that's not the only reason skaters can glide so smoothly, because there would need to be an extreme amount of pressure if that were to be the only thing. This is also physics-based as well, because force equals pressure over area, which is why this works.
There are also aspects of friction and heat that cause the ice to melt. Another important factor to consider how figure skating works is that a skate can glide over the ice because there is a layer of ice molecules on the surface that are not as tightly bound as the molecules of the mass of ice beneath. So essentially they're semi-solid.
These molecules are in a semi-liquid state, providing lubrication.
Okay, enough skating. We should probably go back and get our lab going and show them how it works in an actual chemistry atmosphere.
Awesome! So before we even start this lab, let's cover how to be safe while doing it.
We're working with some pretty cold stuff, so if your hands get cold easily, it might be a good idea for you to wear winter gloves.
Also, don't forget to wear your goggles every single lab you do.
So, what we're going to do with this lab is we're going to take a big block of ice and we are going to have a wire passing through it. The wire is going to have weights attached at the bottom, so that increases the pressure.
To do this, we have suspended the block of ice with ring clamps. Now let's see what happens when we place the wire on the block of ice.
Here we see the wire passing through the ice by using pressure to lower the melting point, allowing it to go through the block. As you can see, the block of ice is still in one large piece despite the wire cutting right through it.
This is because the weights pulling on the wire increase the pressure directly under it, melting the ice block, which allows it to pass through the ice.
And the reason it's still in one piece is because the water refreezes once the wire has passed through, since the pressure decreases.